Do you have your coffee? Because you're going to need one for this. This is the big one, the pièce de résistance, the most accessible proof that we can find for undergraduates that pi is irrational. The most accessible proof that we can find that pi is irrational that doesn't boil down to here are the first billion decimal places and there are no repeats. So it is unlikely that the number is rational. So one moment, please. Okay, sorry. Let's do it. The proof starts surprisingly simply and then gets really weird in a hurry. We're going to suppose that pi is p over q, where p and q are positive integers. Q, yes, so q is not 0. Yes, yes, yes. P and q are positive integers, and the GCD of p and q is 1. So pi is a positive number. We know pi is a positive number, so p and q are positive integers, so this takes care of the fact that q is not 0, and p over q is in lowest terms. So then the proof makes a hard right turn. In fact, this proof makes several hard turns, and you go, what is that there for? But we'll do what we can to explain some things along the way. Also, I'm going to go through this way faster than I would in class, and it's still going to be way too long. But at least you can pause and grapple with ideas with a video in a way that in class we'd have to do with people raising hands and such like that. So we're going to consider the following function. We're going to consider the function f sub n, where f sub n is x to the n times p minus qx to the n over n factorial. What? What? So this p and this q are this p and this q. So we've assumed that pi is p over q. So now this p is set and this q is set. This n is a positive integer. And so this function depends on n and p and q. It is a function of x. So this is f sub n. We may refer to it as little f just for convenience. And we set up this function so that we can set up another function that refers to this function, and it just gets weirder after that. So, because pi is p over q, the following are equivalent. So f sub n is x to the n times p minus qx to the n over n factorial. But there are like 4 other ways for us to write this, and they're all convenient in some way. So p is pi times q, so we can write pi q minus qx to the n over n factorial, and then we can factor out that q to the n. And that might be helpful to us at some point. Or we could recognize that q is p over pi. And we can suck that p right out of there. 1 minus x over pi to the n over n factorial. All of those are the same. all of those are equivalent. You can confirm all of that. Oh, golly, that is just hideous. Okay. Okay. So the more choices you have, the more you can do. So time to make some observations. Some observations. If we multiply through by n factorial, if we just look at the numerators, that is to say, uh, the numerators are polynomials with integer coefficients. I mean, p and q are integers, so we can raise things to powers. Pi times q is an integer. Pi is rational. But because this one is a polynomial with integer coefficients, all of these are polynomials with integer coefficients. They're all the same. And it, again, looking just at the, oh, nope, nope, nope. Let's look at the numerator if you substitute pi minus x in place of x. Well, if you do that, let's see, put a pi minus x where the x is. P minus q times pi minus x whole thing to the n, right? And a little bit of algebra here, a little bit of algebra which isn't even too difficult. Eventually, you get to p minus qx to the n times x to the n, and that's the same thing as what's currently in the numerator. So the numerator with pi minus x in is the same as the numerator with x in. And that means, because the derivative of this is -1, that means that the nth derivative at x is related to the nth derivative at pi minus x, but you've got that factor of -1 to the n to deal with. Still observing. If x is between 0 and pi, then f of x is non-negative and less than or equal to pi to the n, p to the n over n factorial. That's using this right here. If x is positive and less than pi, then this is some fraction to a power, so it's less than or equal to the x to the n, p to the n over n factorial part. For derivatives that are not as high in order as the nth derivative, the jth derivative evaluated at 0 is the jth derivative evaluated at pi, and both of those are 0. And for orders at the nth or greater, the jth derivative evaluated at 0 is the -1 to the j times the jth derivative at pi, and importantly, those are integers. So for even powers, for even orders that are at least as high as the nth order, because remember, n is an integer, it's a positive integer, the jth derivative at 0 and the jth derivative at pi are the same. For odd orders that are at least as high as the order n, they are opposite of each other. And all of that can be gained from looking at those expressions of f sub n. Okay? Now, let capital F sub n of x, same n, let capital F be little f minus the second derivative of little f plus the fourth derivative of little f, and so on until the last one is the 2nth derivative of f times -1 to the n. Side note here. Side note, that's the end. And it has to be the end because remember about little f. Little f, that's an x to the n, that's an x to the n. This is a polynomial of degree 2n. So after you take the 2nth derivative, there's nothing after that. So this is the end. From our last two facts about f, from these last two observations, we notice that capital F at 0 is capital F at pi, and both of those are integers. And notice that capital F plus capital F double prime, both based on n, is little f sub n. Capital F plus capital F double prime is little f. And you can figure that. You can take capital F double prime yourself and line them up and add them up, and sure enough, everything cancels out with that. So this is all the setup. Like, this all gets us going so that we can do the serious work. Right? So what now? Consider capital F prime of x times sine x minus capital F of x times cosine x. Why? Why would we do this? Why? Well, watch what happens when you take the derivative of that. F prime, and I'm just going to get deliberately sloppy here and leave out the little n's. Watch what happens when you take the derivative of that thing, right? In fact, you've already hit the pause button to give it a shot. Right? You're like, oh, I know where this is going. Oh, I know where this is going. Right? You're like, I know where this is going. those are gone. You got capital F double prime plus capital F times sine x. But wait a minute. Wait a minute. Capital F plus capital F double prime is little f. Therefore, the derivative of this is little f times sine x. Well, if the derivative is that, then it follows that the integral, let's go from 0 to pi, just for sport, of little f sub n times sine x dx is, so how does this work? We take an antiderivative, sub, and subtract. That's capital F prime of x sine x minus capital F of x cosine x, evaluated between here and here. So that's capital F prime of pi sine of pi, capital F of pi cosine of pi minus capital F prime of 0 sine of 0 plus capital F of 0 cosine of 0. So what's that? That is f of pi plus f of 0, right? Now we don't know what f of pi and f of 0 are, right? Like we don't know what f of pi and f of 0 are. I don't see anything here that tells me what f of pi and f of 0 have to be. Except that f of pi and f of 0 should probably be integers, right? I mean, f of 0 is definitely 0. And f of pi, well, that's gotta be, right? So this thing is an integer. But the integral from 0 to pi of f sub n sine x dx is less than or equal to the integral from 0 to pi of pi to the n p to the n over n factorial dx, and that's less than or equal to pi to the n plus 1 p to the n over n factorial, because remember that's a number, so like we know how this goes. That's a number. We're just the integral of a number is pretty straightforward. So we remember that n is a variable. It's not a variable in the function little f, but it is a variable for us. It is a variable for us. It's not a variable in the f sub n. Once we decide what n is, then f sub n is defined. But for us, n can be anything, any positive integer. Thus, there exists an n such that pi to the n plus 1 p to the n over n factorial is less than 1. Why? Because you and I both know that the numerator is an exponential function in n, and the denominator is a factorial function in n. And you and I both know from our studies of power series that factorial functions grow faster than exponential functions do. And so eventually, factorial is going to take over. Eventually, the factorial function will be greater than the exponential function. And when that happens, this fraction is less than 1. So the integral has to be an integer, but it has to be positive and less than 1. And this is the contradiction. The integral has to be an integer, and the integral has to be less than 1 and positive. It cannot be. It cannot be. So this is the great proof that pi is irrational. We would never run this by a class. We would probably not run this by a Calc 2 class. They would cry a lot. So we would not do that. But you and I can say to our students that we have seen the proof and we trust the proof because we can understand each of the pieces along the way. And so then we can say to our students, look, we are not just appealing to some higher authority here. We have seen the proof. We know that it works. We've seen the contradiction. And so we believe that pi is irrational, and it's just beyond the scope of what you've studied. That's the big key here. I hope you have enjoyed the time. It's been a lot of time. Thanks for sticking with us.